So the first type of induction problem related to our idea of series and creating formulas for the sum of the series. But the actual method of induction, it's an idea. The idea being I'm going to assume it's correct and then using that assumption prove the next case is correct and then inducing a solution. So we can use it for other sorts of problems. When you look at this question, it kind of is obvious that it must be true. I mean, n times n plus 1 times n plus 2 is divisible by 3. Now, it must be true. Because if you've got 3 consecutive numbers and multiply them together, one of those numbers itself must be divisible by 3 if they're 3 consecutive numbers. So it must be true. But looking at it and saying, oh, well, it's obvious, is not good enough for a proof. So we're going to prove it using our induction idea. So the first case, I'll try it when n equals 1. So we'll get the first 3 consecutive numbers. So we don't really have a left-hand side and a right-hand side for this one. So I'm saying, all right, well, if I get the first 3 consecutive numbers, 1 times 2 times 3 is 6. And sure enough, 6 is divisible by 3. So that's not a problem. So yes, it does work for the first 3 consecutive ones. I'm going to assume it then works for any 3 consecutive, and I'll start with the first one being k. So what I'm going to say is k times k plus 1 times k plus 2. Mathematically, how do I say is divisible by 3? So what I do is I say, well, that's going to equal 3 times some whole number. If it's 3 times some whole number, then it must be divisible by 3. And I'll just call that p. And p, as I say, is a whole number, so it is some integer. I'm then going to prove it's true for the next case. So if I get k plus 1, k plus 2, k plus 3, multiply them together, again, is equal to 3 times some number. Now notice, I don't call this one p, because to call that 3p instead of 3q would be implying that these two are equal. I'm not saying that, I'm just saying they're both divisible by 3. So q will end up being some integer as well. So that's what I want to prove. Now, this is not a series. So I can't go and say, oh, well, I'll get my assumption and I'll add the next term. It's not that sort of question. I have to somehow work out how am I going to get my assumption into this problem. The assumption, remember, was that k times k plus 1 times k plus 2 was divisible by 3, or is equal to 3p. What I'm going to do, I'm not going to expand the whole thing out. I'm just going to expand out the k plus 3. So if I expand it out, I'll have k lots of k plus 1, k plus 2, and I'll also have 3 lots of k plus 1, k plus 2. But I've now got my assumption. Remember, the assumption was k times k plus 1 times k plus 2. So I can sub in 3p, because I know that, or I've assumed it anyway, is equal to 3 times some whole number. Now if you look at the two terms, there's a common factor of 3 there. So I can factorise and say, well, it's 3 times p plus k plus 1, k plus 2. The question is p plus k plus 1, k plus 2 a whole number? If it is, then I know it to be true. Well, it is. Remember, we said p was a whole number. It was an integer. K is a whole number. Well, if I add 1 to k, I'll get a whole number. If I add 2 to k, I'm going to get a whole number. If I multiply 2 whole numbers together, I'll get a whole number. And if I add 2 whole numbers together... So, yes, q will be an integer. It will be a whole number. So, it's proven. I've been able to write it as 3 times some whole number, some integer. So, hence the result is true, if true for k, and then we go and induce our solution. Well, we proved it was true for the first case, so it must be true for all the other cases by induction. A little bit different this time. I'm not getting consecutive numbers or things like that. It's just 3 to the power of 3n plus 2 to the power of n plus 2 will always end up with a number that's divisible by 5. That's what we're trying to try and prove here. Okay. Well, let's try n equals 1. Let's see what happens. And 3 to the power of 3n becomes 3 cubed. That's 27. 2 to the power of n plus 2, 2 cubed. That's 8. 27, 8, 35. So yes, it does work for n equals 1. So that's divisible by 5. So I'm going to assume then it works for n equals k, where k is some integer. Again, I'm going to call it 5p. I can write it as 5 times something. We want to prove it's true for k plus 1. So it'll become 3 to the power of 3k plus 3 plus 2 to the power of k plus 3. I want to prove that's equal to 5 times something, some whole number. Okay, let's start with our... Now I need to get my assumption in there somehow. I can't get the assumption straight in. What I do is something like this. I pick one of them. I've chosen the 3. If you have a look at the assumption, in the assumption we have 3 to the power of 3k. We also have 2 to the power of k plus, was it 2? K plus 2. Okay. I want to get either one of those. I've chosen 3 to the power of 3k. So I can rewrite the 3 as 3 to the power of 3k times 3 cubed, which is 27. I can now substitute my assumption in, but rewritten. So if you have a look at the assumption said 3 to the power of 3k plus 2 to the power of k plus 2 was equal to 5p. I've just rewritten it and made 3 to the power of 3k the subject. And said 3 to the power of 3k is equal to 5p minus 2 to the power of k plus 2. It's still the same assumption. I've just rearranged it. Okay? So let's now play around with that. See if we can get what we want. Now, if I expand that out, 27.5 is 135. I've got 27 lots of 2 to the power of k plus 2 plus 2 lots of, 2 to the power of k plus 3. We want to end up with an expression that's 5 times something. I've got a factor of 5 in 135, but I haven't got it in 27. I'm going to rewrite my 2 to the power of k plus 3. 2 to the power of k plus 3 is 2 lots of 2 to the power of k plus 2. So I've got negative 27 lots of 2 to the power of k plus 2, plus 2 lots of 2 to the power of k plus 2. Negative 25 lots. I've now got a common factor of 5. So I can factorise, and I have 5 outside of 27p minus 5 times 2 to the power of k plus 2. The question is that a whole number? And again, the answer is yes, because we have assumed p is a whole number. We've assumed k is a whole number. Raise 2 to the power of a whole number, I'll get a whole number. Subtract whole numbers from whole numbers. So yes, that is 5q. Q in this case turns out to be 27p minus 5 times 2 to the power of k plus 2. But we know that will be a whole number. Hence, the result is true for k plus 1 if it's true for k. And then we can induce our proof from there. Still in 6n, but a couple more induction questions to have a look at that involve divisibility.